So we studied Q function in previous time. So Q is a quality of action, quality. It's a based on quality. It tries to assess quality of action. That is the, so it seems like similar to the value, right? Value is the expected cumulative summation of reward. That could be somehow related to quality of action. So the value is but a function of state or quality. Q function is a function of state and action. So we will first recap value function and recap Q function, and then we study deep Q function. So this slide is from previous slide, lecture 4 or previous time. And here is the definition of value function and Q value function. So the value function here, V at state S is a function of state S. State is from its name, like position or velocity or current status of some agent. That is the state S. If value function at state S is the expected cumulative reward from following the policy from the state S. So here is the mathematical definition. It's from its name. From its definition, it's a function of state S, and then just expected cumulative reward. Gamma is a discount factor, right? Gamma is typically like 0.9 or 0.99. And R is a reward. R is reward. So let's, there can be some probability of the, how can I? Okay. So expectation, we can rewrite this one like gamma 0, R 0, and P 0, gamma 1, R 1, P 1, gamma 2, R 2, P 2. Right? That is this definition of expectation. P is a probability. So it's like considering probability. It tries to get cumulative reward from the following policies from state test. That is the value function. And what it means is that how good is the state? Because the higher reward, the better, right? The higher reward, the better. So if the value function is high, then we can say that input state S is good, right? Because it has high reward, right? So the value function is about how good is a state input S, and if the value function's value is high, and then we can say that the state is good. And that is the value function. And another one is Q value function. Different from the value function, it takes S and A at the same time, state and action. Q value function at state S and action A is the expected cumulative reward from taking action A in state S and then following the policy. It's almost the same, but the difference is that we just have additional argument action. So that we can, from this value function, we can make some 1D table, right? 1D table. For each state, we can fill some numbers with the value function, but for Q function, we can draw a 2D graph, 2D table as a 2D. We learned this by tabular reinforcement learning. We can fill numbers in 2D table, like if we are considering the Q value function. Mathematically, it's the same. So what Q value function means is that how good is the state action pair? So given state S, and it tries to sum action, like rotate your elbow 60 degrees, rotate your wrist about 30 degrees, that kind of thing could be an action. And then given state S, and then you try to perform some action, then we can assess the quality of the pair of state S and action A. That is the Q value function. Q is the quality. mathematically it's almost the same, but value function, it only considers state S, and Q-value function, it takes state and action at the same time. And let's try some example. So as we, okay. Okay. So we have expectation, right? Then it means that we could have some probability. This one probability. We could have probability. So depending on the environment, it could be deterministic environment where an action deterministically determines next state. There is no probability. So that means probability is always 1. Probability is always 1 in this case, right? So that it makes some calculation easy because probability is always 1. And let's say the RSA, this is a reward. R is reward function. State and action. It's -2 if entering state 0. 3 if entering state 5. These are state indices. State indices. And 7 if entering state 6, and 0 otherwise. And this count factor, gamma is 0.9. And let's try this example. So these arrows are just action. So actions are given. For each state, as I said, each box just represents state. And for each state, action is given. These blue arrows are action. Right? So this shows the action. And how can we get, so these are value function. So the answer is this one. So let's try this one. So we learned value function. The definition of value function is this one. You should remember this one. Just a cumulative reward from following policy from state S. That is the value function. And then how can we get this number? So here, if entering state 0, that means this one has action which enters to state this state, right? And then it has reward 3. But this one action is just stay in this state. That means it is not trying to enter state 5. This is state 5, right? So we have reward 0 because it is about the otherwise situation. But here the action is entering state 5, right? So that we have and then cumulative reward function, right? And then so that the first one, gamma 0, reward 3. There's deterministic environment means there is no probability, so that we can just ignore probability, and then gamma 1, and then here reward is 0, right? Reward 0. So that means value function is 3 for this state, right? This is the first one, gamma 0 is 1, and 3. It enters to state 5, which means the reward is 3. And then next reward is gamma, we have gamma 0.9. And then reward of this state is 0. We already calculate this one, right? The 0. So that we have value 3. So here, that is the reason why we have this 3. And then here, it is the same. It's same as this one. It is included. It belongs to this case, so that reward is simple. Value function is simply 0. And then how about this one? So action is given, right? It goes to right. So then this one could be gamma 0 and going to this state. So going to this state. So this one, this state 0, state 5, and state 6. But this one is, belongs to otherwise, right? This state is not belongs to state 0, 5, and 6. So the first one, reward is 0, and then gamma, and then we have 3, right? We have 3, because the action is already given. So that we have this one. And then gamma square, 0. So that 0.9 times 3, which gives us 2.7. That is the reason why we have 2.7 here. And let's get back to here. It is the same. It belongs to this case, otherwise. So we have value of 0. And then this one. How can we get this one? Minus 2. Here we are 0, and then reward. If enters to state 0, entering state 0, we have reward minus 2. And then gamma, and then we are at here, we are at this state, and then the reward is 0. So that we have minus 2. There is a reason why we have minus 2. And this one, first we goes to state, this state. This state is just 0, right? Reward is 0 because it belongs to otherwise. So 0 plus gamma minus 2, right? So that we have, this one, 0.9 times minus 2, that becomes minus 1.8, right? That is the reason why we have minus 1.8 for this state. So this one is, these numbers are value function. It's just a value. And we can simply follow the definition of the value function in previous slide. Is it okay? Good?
How were the actions for each cell decided?
Sorry?
Like the actions for like the direction of the arrow, how were those decided? Is that random or?
So we have action here. Blue arrows are action.
Yeah, so how were they decided?
Usually, it is a little bit complicated, but for this exercise, we just assume actions are given. But in real environment, we need to consider lots of things to decide actions. Usually, so actually, it is a little bit some very easy example. I mean, for example, in typical, for the Q learning, I will explain later, but in Q learning, we first get value function, we first get Q function, and then we perform argmax to get optimal action. So in advance, assuming actions are given is nonsense, actually. It does not make sense, actually. And let's try different actions. So the red ones are action. And these are just value function. So how do we get these numbers? So these are the same, right? These are the same. Because they belong to otherwise, so that's 0. And then here, 7. So this one is gamma 0. And reward is 7, right? And gamma 1, 0. So that we have 7. And this one, action is given, going right direction. So that gamma 0, 0 plus gamma 1, 7. That means 0.9 times 7, 6.3. And here, it's the same, right? Just simply multiply 0.9 times 0.63, 6.3. That gives us 5.67. This one also. 0.9 times 5.67. That gives us 5.103, right? Actions are given. We can simply follow the definition of value function, which is described in the previous slide. And so here we have another environment, which is a stochastic environment. So in the deterministic environment, we assumed in deterministic environment, probability is always 1. So we do not need to take care about some complicated things in expectation. Because in expectation, all the probability are 1, so that we just simply ignore all the probability. But in real world, most of the environment are stochastic because we cannot consider all the random variables. So there will always some probability. So that in stochastic environment, how can we get these values? So the figure looks a little bit complicated, right? So here, these are just reward. So in previous one, in previous slide, we have given actions, right? We have given actions. This figure, this figure and these figures are different. In the previous example, we assume the actions are given, but in this example, we do not assume actions are given. So it tries to give us reward for all action, right? These are just the numbers are reward, and these arrows are action. So it gives us all possible actions and corresponding reward in this figure. So the previous one, we assume actions are given, but here we do not assume actions are given, which is more realistic setting. Let's try this one. So these are state indices. And suppose we have probability here, because we are in stochastic environment. So probability here. From state S4, this is state S4, right? State S4, probability of going to state 6 is 0.5, and from state 4 to state 5 is 0.5. That is our assumption. This count factor is 0.9. What is V star S4? So star means optimal value function. We studied optimal Q function actually. We did not study optimal value function, but it's almost the same. We studied optimal Q function, which is from previous slide, Q star. Q star is just assuming we have, we maximize the expected cumulative reward function, right, for all possible time step. And to this step, we need to get some pi policy that can maximize this Q function. That we can rewrite this one. We can rewrite this mathematical formulation to like this one, which is called Bellman equation. So here we have a reward from the state action and current state and action. And then we have next one. We have like this one. This is current one. And there can be many possible S prime and A prime. And then we will choose a action A prime, which can maximize Q function of next time step with this count factor. That is what Bellman equation is saying. So we can rewrite this one to this one, which is called Bellman equation. So we learned optimal Q function in previous slide, and then we will simply extend it to optimal value function in this example. So how can we get V star S4? So here we have S4, right? We have S4. So here are answers. So V star S4 is 5. How can we get this? This one S4, V star S4. So according to this definition, we need to first get reward, right? Expectation and reward. So that from this state S4, we can perform this action, right? Because these are two probability, so that we can get like a reward, gamma 0, reward and probability 0.5 plus reward, gamma 0, 7 probability. That gives us 5, right? That is the reason why we have 5 here. Once we get to the state 5 and state 6, then we have just the infinite loop, so that we can ignore these Q functions, so that we can ignore the followed Q function and then just simply consider the first reward, right? So that from this definition, we can just simply get this, the expectation. The expectation means we need to consider all cases with probability, and there are two possible probabilities, right? Two possible actions. So for each action, which goes to state 5, we have probability 0.5, this one, and then for another one, which is go to state 6, we have state 7, reward 7, and probability 0.5, so that we have optimal value function of state S4 is 5. The answer is 5.
But can we also also go to state 3 from state 4 according to the diagram at the top.
State 3 to state 4?
State 4 to state 3 according to the diagram at the top because there's an arrow toward the left side.
So, but the here we have probability here, and then this probability says that from state 4, we only have these two cases, right? So that this one is the optimal value function of state 4, and then how about this one? 4.5. 4.5. Then we have this one 5, and then 4.5 means this one, and then we can go to this one, and then, but actually we do not have probability. We do not have probability, so that let's assume our remaining probabilities are just 1, and then gamma 0, and then reward is entering this state is just reward is 0, right? Entering this state reward is 0, and then probability. We do not have probability. P as 4 plus gamma 0. Entering this state is also 0. P as 2, and then gamma 1. And let's say we are at here, and then our reward is 5. No, we already calculated this value function, right? The optimal value function. So in previous slide, once we have optimal value function of next one, we can just simply use this one without calculating it again, right? So that we can simply use gamma and 5, right? I'm not sure how to cancel these probabilities. Let's assume our action is just no. So that this is the optimal value function. So that if we goes to left direction, then the value should decrease, right? We somehow know that let's assume we somehow know the global structure of the graph, and then the reward goes to -2 if we goes to this direction, right? Reward is smaller than going this direction, so that we can ignore, where is it? We can ignore this -2 direction, and then just simply focus on this one, so that we have this one, which gives us 0.95, which is 4.5. So that we have 4.5 here. Remaining are the same, just simply multiplying 0.9 to 4.5, 0.9 to 3.64, so that we can simply get the optimal value function for our state. It's okay? It's a little bit complicated, so I recommend you to recap these examples so that you can understand what are value functions. So definition, at first glance, it looks really simple, but if we try this exercise, it might be not very trivial to apply this equation and definition to the real exercises. So it's better try this exercise with your hand and understand what Batman equation is saying and what is the why Batman equation is famous and what is widely used, so that you can understand this kind of thing if you try this exercise with your hand. So far we recapped the value function, and then we can proceed to Q function. As I said, the difference between value function and Q function is that we additionally take action A into account. So it's like in casual word, the Q function definition is the total discounted reward of taking an action A in state S, assuming all future actions are optimal. That is exactly consistent with this, definition, right? Assuming remaining things are all optimal, and then we just simply get total discounted reward of taking action A, assuming all features are optimal. That is the optimal Q function, optimal. And mathematically, we can just simply rewrite it like this one. So that, we need to get maximum Q value, which makes a maximum Q value with the optimal action. And once we get Q function, this is just a Bellman equation. Just a different formulation of Bellman equation. And the importance of value function, Q value function, is that if we can calculate Q value function for all possible combinations of state and action, then what we can do is that from current state, we can know which action is optimal, right? That is related to your question, in previous question. Once we have Q value function for all possible combinations of state and action, let's say we have a 2D table, and then state, action, and then this is a Q function, and then assume we filled all numbers. We learned Q function, and we fill all numbers in this table, and then from state S, current state, let's say current state is this one. We can simply pick a action which can maximize Q function among this candidate, right? That is the optimal action, and that is the action that this agent needs to take with current state S, right? So that we can, because the definition of Q value function is that this the total discounted reward of taking an action. So defining reward is up to you. So definition of reward is also important. Which reward are you going to introduce is very important. But once you define reward function, then once we know Q function, then which action we need to take at the current state S can be simply obtained by performing argmax function in this table, right? So insight is that if we know Q function, if we know optimal Q function, we can compute the optimal policy pi star. So as I said, policy is taking state as an input, output action. So let's say some agent is walking around and it saw something, it collides with some object, and then in this current status, it collides something. Then which action it needs to do can be easily obtained if we have a optimal Q value function. Of course, there are many limitations in Q value function. For example, first of all, getting optimal Q value function for all possible combinations of X and A is very difficult. And another thing is that it assumes state and action are discrete, right? It assumes state and action are discrete, right? So we can see like this one. So for all it assumes there is some predefined possible state, large S, and then it tries to perform argmax. Performing argmax means that Q value function is in discrete space. But in real world, discrete means going. There are some. Discrete and continuous. Discrete means like going left or going right, forward and backward. This kind of non-continuous actions. But the continuous, just rotate your hand 30 degree, your hand 30.5 degree, 31 degree. The numbers are continuous, right? So the actually Q function, Q learning, all this stuff assume state and action are in discrete space. That is the actually limitation of Q learning when we apply this kind of Q learning to robots. So unfortunately, Q learning is not. People do not try to introduce this kind of Q learning in robotics because the action space of robots is continuous. But by nature, the Q value function assumes actions are in discrete space. So that is the discrepancy. And then we will also learn how can we do something with the continuous action learning in later. But this one is the used in many traditional reinforcement learning examples. And inside is that if we know optimal Q function, we can compute optimal policy pi star. I mean, policy is always important. Given state S, in inference stage, let's say our agent has a state S, and which action needs to perform is the most important thing, right? So that policy is always the most important one. But instead of getting policy network directly, it tries to get policy network indirectly by first getting optimal Q value function and then performing argmax at the Q value function. So that we have optimal policy network. That is the spirit of Q value function. Then the question is how to get optimal Q value function. I mean, okay, I understand. So if we know Q value function, optimal Q value function, then we can get optimal policy network or policy function so that we can employ our agent in some random environment. Okay, it's good. Then how can we get this optimal Q value function, Q star? So there are a couple of algorithms to get optimal Q value functions. The first one is brute force way, very naive way. Let's see this algorithm. So the inputs are discount factor and initial state S, right? And then we initialize Q as a table array. That means as an AR discrete space. We assume 2D table. That is the initialization of Q value function. And then we repeat this one. Simply repeat this one. First, we take a random. So we have initial state, right? Let's say initial state is like this one, state 0. And then we have like 1, 2, 3, 4, 5. We have 5 possible actions, right? Among 5 possible actions, we just take a random action. And then we have received some reward. We have predefined reward function so that we can calculate reward with the initial state as 0 and randomly take an action A. And then we observe a new state. We perform some action, right? We perform some random action so that it changes state, so that we have the new state. And update Q and S according to the Lemon equation. Q, S, and A. It's just R is here, reward, and then here, and then so here we have a Q value function. So that let's say we have we randomly chosen this one. And then this one. How can we get this one? So and then we have it changes current state S to, let's say, state 1. Then we are talking about this row. Among this row, so firstly initialized to 0, 0, 0. All numbers are just simply 0. And we can just simply get maximum Q value, but at the first stage, numbers are always 0. So it becomes 0, and then we can just simply write this cell with the reward R. And then we repeat this, infinite loop, we repeat this. Just some similar to just simply visit some, just randomly visit some cell, and then we have some reward from the predefined reward function, and we have updated state, and then we visit another row because we have updated state, and then we just simply take some Q function among possible S and A pairs, right, for the updated state, and then we simply update this zero initialized numbers to some numbers, and then we just repeat this. That is the brute force naive way to get Q value function. Is it good? Okay, clear? Feel free to any question if you're not, if you feel some unclear thing. You can ask in Korean, so don't be afraid. And So from this, we know that it always takes a random action, so that it looks like very slow, right? It looks very slow. That is true. It's really slow. It always takes random action. It always takes random action, so that, for example, if you are in maze, let's say you are in maze, a very complicated maze, and then you are here. This is you, and then this is the final goal. Even you are at the very close to the goal, you always take random action. That is the problem. You always take random action, so that although you are almost at the end of the goal, very close to the goal, you take random action so that you lose the chance to update for this state. From this is you, and this is goal. Without random action, maybe we can just choose some pre-calculated Q function instead of always take a random action. Then maybe in some case you can just, in lucky case, you can just take action at here. Then you can simply finish the algorithm because you reach the goal. But the problem is that you always take random action, so that it makes convergence really slow. And if the number of possible states and possible action are many, then it becomes really slow, right? But anyway, if we have enough time and enough cost, then we can, with this algorithm, we can maybe get some optimal Q value function with enough number of iteration, right? That is the first algorithm. And second algorithm, of course, try to address this kind of always random action thing. So the algorithm 2 is called epsilon greedy online learning of optimal Q. So the first algorithm is the online learning of Q function, and second one is epsilon greedy online learning of Q function. So the difference is that we have epsilon greedy. So inputs, we have additional input, greediness parameter epsilon, which is in the range of 0 to 1. And this one the same, just we always draw a 2D table, SNA table, and then why should we repeat this one? But it looks a little bit different, right? So with probability 1 minus epsilon, take greedy action. You know greedy algorithm? In algorithm class, you might have learned the greedy selection. Without global prediction, it just tries to get some local prediction with the immediate high reward, right? It is the greedy approach. It's the same. So that is the greedy thing that we are try to talk in this algorithm as well. With probability 1 minus epsilon, we take greedy action A, like this one. So we have Q here, and then at the first, all numbers are initialized as 0, right? But after some iteration, some numbers are filled, right? Some numbers are filled, and then with some probability, we take instead of taking always random action, we just simply take some action which maximizes the Q value function. Otherwise, with probability epsilon, take a random action. So there are two cases. With probability 1 minus epsilon, it tries the greedy solution, and then we call this exploitation, what we've learned. So what we've learned is that some numbers are filled in this table. We try to use it. Exploit means, just the same word are used, utilize. It tries to use what we've learned so far. So it is called exploit and explore trade-off. If the algorithm is biased to exploitation, then it loses the chance to explore new actions, but it will stuck in local minima. If the algorithm is biased to explore, which is the first algorithm, that convergence is really slow. But there's a trade-off between exploitation and explore. That is an epsilon, hyperparameter epsilon determines the trade-off between exploitation and explore. Remaining things are the same. How can we how we choose the action is different. With some probability, we take greedy action, which maximizes Q function. Otherwise, just the random action. Remaining things are the same. We receive reward and observe a new state and update Q and S. This one, these are the same. People call this exploitation. Explore. Trade-off. Bias to explore is algorithm 1. Always exploitation, no random. As we do not have explicit target for reinforcement learning, we always need to encourage system to explore something. Actually, it can learn learn useful things from explore. It fails in environment. It sometimes succeeds in real environment. So that we always need to encourage our system to explore the environment, because we do not have explicit target in reinforcement learning. So that we need to always take care about this trade-off between exploitation and explore. This kind of trade-off is always applicable to later algorithms. Is it good? Okay. And let's try this Q-value function example. So the numbers are the same as the previous one. The numbers are the same. And the question is, actually it's a question for you. Which set of blue arrow roughly correspond to Q star SA? Can you try this? No? Now it's 11:20, so let's think until 11:23. Anybody think A is the answer? Raise your hand. A. B. It seems just people try to raise hand with many people. C. What about people without raising hand? Okay, the answer is C. So this one shows the reward. Left one is the reward. It's the same as the previous examples. And then we have value functions here, right? The optimal value function. So that here we are, optimal thing is that, what is the optimal value function for state that's 4? State that's 4. So always try to maximize the, we want some maximum cumulative reward, right? So among 3, so we have 2 possible, we have 3 possible actions for state 4, right? Going left, going up, going right, and then according to this one, reward is 0, 3, 7. So we choose 7. So that is we have 7. And then here, we have discounted, and then here, here. And then we can multiply 7 with 0.9, so that these green numbers are just value function, optimal value functions. And then given this optimal value function, it is easy to calculate optimal Q value function. So for example, the difference between, so of course A does not make sense because it is just simply the same as the reward, right? So A is definitely not the answer. So between B and C, let's think B and C. Difference is that this number, right? These top numbers. So let's say we are at the state 4, and then action is going left. Then then reward is 0, right? Reward is 0. And then we have discount. Here we discount. And then we have value function here. That is the reason why we have this one, right? 5.67. And these are the same. Just we can simply introduce this definition of Q-value function to get the correct Q-value functions. So the answer is C. And this one also shows how can we apply this algorithm 1. The first algorithm we learned, right? Just a random, always take random action. We can simply see how can we introduce algorithm 1 when we try to get optimal Q value. So as I said, we have a 2D table. These are the state, and these are actions. And then all numbers are just 0, initialized as 0. And we first randomly chose, let's say initial state is state 3. This is initial state. And we randomly chose this action, going right. So how can we get this number? 0. What is this one? I think this one is A prime. This one is A prime. So we have randomly taken action, going right, 3, and then going right, reward is 0, so that we have reward 0, discount factor, and then from next state, state 4, all these numbers are 0, right? All these numbers are 0. So any action you choose, Q-value function is always 0, so that we leave this number as 0. This is 0. And how about this one? And then we are state 4, right? Because we are at the next state is state 4. And state 4, we randomly take going up as an action. Then state 4, and then going up. Then we have reward 3, right? This one, reward 3. And then discount factor, this one is prime. And then from state 5, all the numbers are 0, right? So no matter which action you choose, numbers are always 0. This one is always 0. So that we can update this number as 3, right? So that is how we apply algorithm 1 when tries to get optimal Q function. We simply randomly choose action for next state and then calculate this one. Let's try this one as well. And then we have updated number, and then let's say we are at state 3 and then going right. State 3. We are state 3 and going right. Reward is 0. Then we have 0 and discount factor. And then next state is state 4. So, but we have maximum is not 0 now, right? If we take going up as a action, then Q function is 3. So that we have 0 plus 0.9 times 3, that gives us 2.7. So that we update this number as a 2.7. We keep repeat this until we reach to the predefined number with total iteration. So when we repeat this again, then maybe we can reach to the Q-value function, optimal Q-value function. But as I said, the required number of iteration might be too high. Convergence could be really slow for the algorithm 1. So why we do this? Why we do this kind of complicated things? The answer is this one. Once we know optimal Q function, we can compute optimal policy pi star. So that in some simple environment and discrete space, we pre-calculate optimal Q function for all possible combinations of state and action. Then we finish analyzing current environment, and then we employ our agent to our environment. Then our environment always can choose optimal action based on pre-computed Q function. Because we can just perform argmax, right? We can just simply perform argmax with this mathematical formulation. So our environment, we first, as I said, the goal is to employ our agent to the environment, and then we can analyze our environment by pre-computing Q function. That is the reason why we do this kind of very complicated things. Okay? And let's proceed to the deep Q learning. It is not very complicated, fortunately. So as I said, Q learning is a function. So Q learning is a function approximating to estimate action value function. So if the environment is too complicated and the possible number of state actions is too many, we cannot pre-compute optimal Q value function. It takes too much time, so that we try to approximate optimal Q value function with function parameter or deep neural network. That is the philosophy of Q learning. Instead of pre-computing all possible Q functions for all possible combination of state and action, we just simply try to approximate Q function because it takes too much time. So this is familiar, right? Just same VM allocation. And how can we train our network? So what we're trying to do is design a network. Design a network that takes S and A and outputs Q. That is our goal. We design a neural network that takes state and action, outputs Q function. And we want to train our network to output an accurate Q function. In theory, if we perfectly train our network, then we can do the same thing. Then we know for current state, let's say we have predefined set of actions, and then we can, let's say, after this is network. And then after training, maybe current state action 1, Q1. State action 2, Q2. State action 3, Q3. Among this one, Q1, Q2, Q3, we can just pick the highest Q value. Let's say Q2 is the highest one. And then from current state S, state is the same. We can perform action 2 for our agent from the current state, right? That is just consistent with the taking argmax, right? But instead of having predefined table, we can just use neural network and then just simply take action with which produces the highest Q value function. How to train this? Because we do not have ground truth Q value, right? So how can we train this? So this is very tricky. So loss function is like this one. Y is the target. This is just output of neural network, right? And then Y is from here. We do not have explicit target of Q value function, so that we just use a Bellman equation. Our reward is from an input SNA, right? From SNA we can compute R, and then this one is, it seems like target is also from neural network. Target is also from neural network, but the difference is that we use network weights of previous iteration instead of current iteration. We use network parameter weights in previous iteration. So target, this one Y is detached in computational graph and use weights of previous iteration to fix the target. It looks very fragile, right? Fragile, and it looks very interesting. So why we do this? So at first glance, it's very non-straightforward to use neural network output as the supervision target. So using previous iterations output for the target, that is the Q learning. So how about in the early? But the problem, the straightforward concern is that in the early stage of the training, the network is randomly initialized and it outputs just the garbage values, right? So that what happens if we just supervise our network with the garbage values from randomly initialized Q function network? That is the concern. So that people invented some ways to address such concern. The first one is true reward. So that from SNA, this is true reward. This is from network output for the future Q functions. But this R is just there's no approximation. R is just we can directly compute reward function from our predefined reward function. So that we use true reward R as an anchor. The actual environment reward provides a ground truth signal, gradually correcting the inaccurate max Q prime estimates. So that we can use this one. So if we train long iteration, then of course at the early stage of training, the Q prime will be garbage values, but true reward is always, we can use such kind of true reward as an anchor so that training will be stabilized. And the second one is high initial exploration, epsilon close to 1. So instead of using neural networks output, so here we use neural networks output as a action, right? Among many actions, we select an action which makes the highest Q function, right? But instead of using neural networks output to choose maximum action, optimal action, we just use randomly chosen action, right? The agent most ignores the untrained network and takes random action to discover true reward. So at the early stage of the training, instead of using the network's output to choose the optimal action, we just choose random action, like the algorithm one, at the early stage of training, because the network is too, it is not trained enough, so that instead of using network, we can just use random action. Of course, making random action, it might introduce some noise, but in some case, it might be better to use this one instead of garbage values from random initialized neural network. And the final one is replay buffer warm-up, which will be introduced in later slide. So network updates are delayed until memory collects enough diverse transition using pure random actions. So we do not have training data, right? So that we instead of updating network at the from the very beginning of the training, we delay the network update until memory collects enough diverse transition using pure random actions. Let me explain this in later slide. I think we need to explore this in next class. So experience replay, I'll explain this in later next time, and then this is all for today. And any question about the Q value example, key value function example?